Okay. The title of today's lecture, Magnetic Fields Due to Current. So in the last chapter, we studied the magnetic force based on the moving charge in the presence of uniform magnetic field. So now what you exactly studied yesterday, if a charged particle is kept in the magnetic field, it will experience the force only if the charged particle will move. If the charged particle is not moving, what will happen? There will be no force. So now, two things we have to get the information in your mind, whether the source of the magnetic field is come from the current or from the moving charge, because both are possible. If the wire is carrying the current, the wire should be surrounded by the magnetic field. If the charged particle is moving in the wire in the presence of the magnetic field, by the time it will experience the force. By the time it will experience the magnetic force. So today, what we are going to do, we are going to discuss only few topics in this chapter. The first thing, we are going to study the concept of Biot-Savart law. So by using this law, we can find the magnetic field, and after that we are going to study the important rule, Ampere's law, and then we are going to study magnetic field generated by a long straight wire, and finally we are going to study the force between the two parallel currents. Actually, we reduced most of the topic in this chapter because I told you, my dear, the time duration was short, and some doctors, because of the extended holidays, we cannot be able to complete all the chapters. So that's what we reduced the number of problems. So based on the number of problems, we are going to discuss the topic from the problems. Okay, so we are going to discuss 3 problems from this chapter. So I have to reduce the content also from this chapter. So first of all, what we are going to do, we are going to study the concept of Biot-Savart law. So in this law, what we are going to do, we are going to study the concept of the magnetic field. My dear, you can just have a look of the diagram here. Actually, here we have a very long, straight, curly wire. That means it's not a straight wire, it is a curly wire. That means it's not exactly perfectly straight. It's just sometimes some places it will be bent, and sometimes some curve will be there. So if you have this type of wire, if you want to find what should be the magnetic field at this point P, how you have to calculate? Because this wire was lengthy, but it is not a straight. So for these calculations, what we have to do, we have to take only a small element ds. That means I'm going to consider only a small portion of the wire. That means a small infinitely small part of the wire. And for that wire, we have to consider how much current will be passing through the wire. And we have to consider what should be the distance from that element to the place, to the point P. And the most important thing, the unit vector also, because for example here my unit vector or unit vector will be different. And for example, if I consider this place, this element, and here the unit vector will be different. That means each and every elements have the different unit or vector. So here what we are going to do, we are going to find, we are not going to find the for the entire length. First we have to take only a small portion of element ds, and in that element ds, how much current will be flowing. That means the current has the vector quantity because it has the direction of flowing. And if you consider only small portion, then the ds element is also a vector because it also is a vector quantity. So that means the 3 important things, this is our formula for Biot-Savart law, because we are going to use this law for the rest of the chapter, rest of the topic, because by using this law only we can find the rest of the formulas. So if you just see this formula, what are the things, my dear? Actually here we have some constant term, which is nothing but mu naught over 4 pi. So this is the constant term. And here the mu naught, it's like our epsilon naught in chapter number 21. When you studied the Coulomb's law, we studied the concept of the permittivity. Am I right? With epsilon naught. But here we are just going to study the concept of the magnetic field. So when you just study the magnetic field, then we have to use the Greek word mu naught. So this mu naught takes the value, it's a constant value of 4 pi multiplied by 10 to the power of minus 7 Tesla meter per ampere. So when we just study the concept of a magnetic field, these are all the constant term. Mu naught over 4 pi is a constant term, but the rest of the elements you have to keep into your consideration: current, and the element, small element from the wire ds, and the most important thing, the angle. So here you have a cross product. When the angle is 90°, then what will happen? Your magnetic field calculation at this point P will be maximum. So first of all, you have to consider what are the things you have in the numerator part and what are the things you have in the denominator. That means top of the equation and the bottom of the equation. In the top of the equations, we have the current element I, and we have the small element from the wire ds, and the most important thing, the angle theta. So that means all these all have the direct relation with the magnetic field. So if the current will be more, then the magnetic field will be more. If the ds element, when you just take the element more, then it also have the direct relation. And the most important thing, the angle. If your angle has 90°, then the magnetic field will be maximum. If the angle is less than 90° or 0, there will be no magnetic field. And also here, the distance is one of the important things. So whenever the distance get increased, what will happen? Then your magnetic field will be decreased because it has the inverse relation. So if you have any question, because generally in the final theory exam, we told you we are going to consider all the theory questions in the type of multiple choice. Previously, we make you to write as a definition form, but for this semester, even the last semester also, we consider, because many students, they requested to give the numerical type, that means the multiple choice question for the theory. So we consider most of the students, they you demand. So by that, we discussed in our group meeting, and finally we consider all the theory question must be in the multiple choice question. So please, my dear, if you have any theoretical question, better please read all the 4 options. So here we studied the Biot-Savart law. Suppose if you got any question from this Biot-Savart law, please, my dear, read the question. Which is your direct relation? Which part is inverse relation? Because last semester, last midterm exam, we asked some question from the Coulomb's law. Some students, you know the answer, you gave the equations very correctly, but when you choose the answer from the options, you gave the wrong answer. Many students, you gave the explanation near to the question, but unfortunately, what happened? The answer, what you choose from the multiple choice question was wrong. So please, my dear, keep the formulas in your mind, and please see what are the things which has the direct relations with the equation, and what are the things you have the inverse relation. For example, in this equation, we have current and the element ds, and the angle has the direct relation. If the angle is 90°, then you will get more magnetic field. And also the most important thing, the distance from the element to the point P. For example, if you consider this element, what will happen? If you consider this point, what will happen? Then the unit vector R will be different. So that means place to place, when you take any small element from the long lengthiest wire, what will happen? Then your unit vector R will be different. But that's not a matter. We are not going to ask any big lengthiest theory question, and all your theory questions must be the multiple choice question, and we give more importance for the numerical type question. But that's not a matter. Just keep the equation in your mind. So if you want to use the Biot-Savart law, we have to find some different equation from the Biot-Savart, because it's a main equation for getting the rest of the equation, because the first title is related with Biot-Savart law. And also, if you want to get the equation, there are 2 ways. For example, you can see we have another equation for the magnetic field generated by a long straight wire. And here also you have a long wire, but it is not a straight wire. When you study the concept of this Biot-Savart law, it is not a straight wire, it's a curly wire. So we have to find this equation. So either you can use the Ampere's law for finding this equation, or you can use the Biot-Savart law for finding this equation. So in 2 ways you can get. If you are using the Biot-Savart law, then the length of the equation will be more. But if you are directly use this Ampere circuit law, it will be very easy. So we are going to reduce the content of today's lecture. So please, my dear, the first most important topic in this chapter is Biot-Savart law. So you must know, if you take a lengthiest wire which is not a straight, so in such a case, if you want to find the magnetic field, you have to consider only a small portion, and you have to specify some point where you are going to find the magnetic field. And I told you in magnetism topic, some places will be marked as dot, and some places we marked as cross. So if you have a dot symbol, that means the magnetic field is coming out of the page. If you have a cross symbol, the magnetic field is going into the page. I already explained these topics in your last experiment, E over M. Clear? So we have to consider one particular point. In that point, what should be the magnetic field calculation for that small portion of the wire? So you have to consider the angle, and you have to consider how much of current is flowing through that particular area, particular element. And the most important thing, if the angle is greater, that means 90°, then you will get the maximum magnetic field. But if the distance will be more and more, what will happen? It has inverse relation. Then your magnetic field will be weaker. Clear? Okay, now we have to come for the Ampere's law. It's exactly similar like the Gauss law. You already studied in chapter number 23 when you study the concept of the charges. So just go back to that equation. So what you studied in that equation, my dear, do you remember that Gauss law? EdA, which is exactly equal to charge over epsilon naught. Am I right or not? Do you remember this equation, my dear? Do you remember this equation?
Yes, yes, doctor. The
So
flux.
it's, yeah, the flux, because when you find the flux, because the left hand side equation is also related with the flux calculation, and the right hand side is also related with the flux calculation, because we solve some problems. In the similar way, if you want to use this equation, you have to find the electric field. But when you just study the concept of the Ampere circuitous law, you can see here we have the electrical field E, but when you just study the Ampere's, you have see magnetic field. And here we have to consider the closed area, but here we have to consider the closed loop, because we are going to consider only the wire. Carry the current is through the wire. So if you just see the wire, only we have the loop. You have to see each and every line surrounding by the wire is called as loop. But in Gauss law, we studied the concept of the area. That's what here we use dA, here we use dl. Just compare and study. And the right hand side of the equation, charge enclosed. What is the charge enclosed in the Gaussian surface? Because you have to draw the Gaussian surface, which is in the symmetric shape. Just go back and just recall. What are the two shapes we consider? Either cylindrical shape or the spherical shape. So how much charge is exactly sitting inside the Gaussian surface? We have to consider the charge. But here we have to consider how much current is flowing through that wire. Multiply by the constant mu naught. Mu naught is the permeability, and here epsilon naught is the permittivity. Clear? So what is this permeability, my dear? What's the difference? What's the meaning for the permeability? It's nothing but if you take any material, if you just put that material, if you got easily magnetized, when you put it in the external magnetic field, it will be easily magnetized. That is called as permeability. So which is represented by the letter, Greek letter mu naught. So just compare and study. So if you want to study the Ampere's law, you have to see this is your magnetic field. This is the loop consider. You have to see the picture. I have a wire, and the direction of the current will be in the upside. You should just see the wire. This is the direction of the current, arrow marks. And if you just using your right hand rule, when you just hold the wire like that, your thumb indicates the direction of the current, and all the fingers curving is indicate your magnetic field. So when you just see this diagram, each and every loop is a closed loop. You should not consider the open loop. When you just apply this Ampere's law, the loop must be closed. And how much current? Because this is a wire, this wire is carrying some current, and surrounding, whenever the current will be flowing through the wire should be surrounded by the magnetic field effect. And these magnetic field lines will never intersect, and it should be the closed one. So if you want to write the Ampere's law, because we are going to use this Ampere's law for finding the magnetic field of the straight wire, and I just have some explanation in the next slides. By the time you will get some clear idea. But the most important thing, we have to use our right hand rule when you just know the direction of the current, and all your fingers curving the wire is nothing but your magnetic field. Clear? Okay, let's become for our derivation, how we got that. So if you are using the Biot-Savart law, we can find this magnetic field for the long straight wire. What's the formula? I will tell you how we got this formula. So if you are using the magnetic, because that derivation was very lengthy, so I don't want to waste the time, because that derivation will go maybe 2 pages. If you are just to first write the Biot-Savart law and applying some trigonometric equation, and you have to do some apply some upper limit and lower limit, and by the time finally you will get the equation of this straight line. So I directly write the answer of the straight line. So what's the value of the magnetic field for the straight line? Mu naught I over 2 pi r. What is this 2 pi r, my dear? When you just see the cross section of the wire, it's like a circle. So what is the distance of this one complete circle? So that means it's nothing but the perimeter of the circle of the wire, which is nothing but 2 pi r. So we know the equation, and here it is a dot product. So whenever you have the dot product, you must have the cosine. So that means here the angle between this magnetic field and the loop is exactly 0. Both are in the same direction, parallel. So that's what your angle is 0. So that means cosine 0 is the maximum. By that you'll get B dl. So in place of this magnetic field, when you apply the value of this formula, what will happen? This mu naught I over 2 pi r is a common term, so you have to take it outside. When you just integrate this dl, my dear, this dl element by element, if you consider, it's like a complete circle. The cross section of the wire is nothing but is a perimeter of the circle. So what's the length of the circle? Which is nothing but the distance. For example, if you see the circle, it is a complete circle. If you just start from this point, when you just end here, it is exactly equal to 2 pi r. The distance from one point to the another point of the circle is nothing but 2 pi r. So when you just differentiate this dl, what you will get? You will get L. So in this place of the L, when you substitute this value, which is nothing but 2 pi r. And here what will happen? This 2 pi get cancelled, and r get cancelled with this r. What will happen? Finally, you will get the Ampere's rule. Clear? This is just for the proof. But no need to write any proof in the question. Just keep the formula in your mind. That means you can get the magnetic field. You can get the magnetic field for a straight line. From that equation, you can find the Ampere's law. Or by using the Ampere's law, you can find this also. So both way you can find. Like in chapter number 22, we studied Coulomb's law and the electric field. By using the Coulomb's law, you can find the electric field for the point charge, or from the point charge electric field equation, you can find the Coulomb's law. So that means it's a reversible equation. From this, you can find that, and from that, you can find this. That means by using this magnetic field for a straight wire, you can find the Ampere's law, or by using the Ampere's law, you can find the magnetic field. So what I'm going to do, I'm going to explain this equation by using this Ampere circuital law, and that was given here. This is our third important formula because we have some questions in this chapter by using this rule. So please, my dear, listen these topics very carefully. It's very easy. So magnetic field for a straight wire, this equation. So how we got this equation? Here we have two cases. You can just see this picture. I have a wire, and I'm just going to draw the Ampere's loop here for this wire. That means you have to see here, my wire radius is r, and my Ampere's loop radius from the center of the wire to this is nothing but small r. So when you just see this diagram, my small r has a greater value than the radius of the wire. So if you have this type of value, if you have your radius which will be greater than the radius of the wire, what will be the case? So I have to use our Ampere's rule, B dot dl, which is exactly equal to, in this place of dl, I'm going to apply 2 pi r, and when you just this 2 pi r, which is exactly equal to mu naught multiplied by I, because the current is flowing through the wire. When you just rearrange these equations, what will happen? You will directly get the equation, because this is very easy. When you are using the Ampere circuital law, you will get the equation for the magnetic for the straight wire. It will be very easy. But if you are using the Biot-Savart law, it will be very lengthy. The only condition, you have to just draw the circuit. That means the loop. The dotted line is a loop like our Gaussian surface. All this dotted line indicates our Gaussian surface. Then you have to apply the condition. What is the condition here? My small r has the greater, because from the center of the wire to my loop, what is the dotted line? Is our circle. This is our loop circle. So my r value has the greater value than the radius of the wire. If you have this type of condition, what will happen? The perimeter of the wire, that means the cross section of the wire, which is exactly equal to 2 pi r. The distance of the wire is nothing but the 2 pi r. And when you apply, what will happen? You will directly get the equation. And another way, you have another condition. If your capital R is smaller than small r, what will happen? Then another case. So in such a case also, you can use our Ampere circuital law and Ampere's circuital law. By that, what will happen? You have to see, my dear, this is our actual size of the wire, and we have to consider the dotted line here. This is our dotted line. Consider this dotted line, and you have to see here, my dear, in this case, I have to consider this is my R, and this is my actual radius of the wire. So in this case, what will happen? My R has the greater value than small r. And in this case, what will happen? The current will be flowing through the outer surface, as well as the loop value. You have to consider how much current will be going through the small loop. So we have to give importance for the smaller. By that, what will happen? The current in the enclosed is nothing but the dotted line, which is exactly equal to the area of this circle and the area of this circle. That means pi r square is nothing but the area of the inner circle, and pi capital R square is nothing but the area of the cross section of the wire. By the time, you can easily find how much current will be enclosed, and I have to take this value. When you just substitute the value here, that means I enclosed. When you just substitute the value of the I enclosed here, what will happen? Finally, you will get this equation. So if you have any question, first of all, my dear, listen the information. Listen, just read each and every point from the question very carefully. What is your actual R? What is your small r? The actual R is nothing but the radius of the wire. And what should be the circle? What should be the enclosed diagram you are going to draw for that wire, which is nothing but, because that will be very, very important. So you have to compare the two radius for the dotted line radius as well as the radius of the wire. You have to consider. So all these informations will be given very clearly in your question. When you just get the info, because we have one question related with this topic, and please, my dear, when you just solve that question, by the time you will get some clear idea. So when you just have your capital R greater than the small r, this will be the case. So here the small r indicates the dotted line, and here capital R indicates the greater line. So that means the magnetic field, listen carefully, my dear, here the magnetic field will be different, here the magnetic field will be different, and even in the surface of the wire the magnetic field will be different. When you just go inside, what will happen? By the time, some small changes, some different answers you will get. So you have to consider what should be the radius value, what should be the radius of the outer circle, what should be the radius of the inner circle. So when you just see the value of these both radius, by the time you will get. But if you just have radius greater than the radius of the wire, by the time you can directly apply this rule. But when the radius of the wire will be smaller than the radius of the, when the radius of the wire will be greater than the radius of the inner circle, what will happen? By the time you have to use this rule. So we have some rules, we have some numerical question based on these two formula. So we have to compare the radius. Clear? And finally, we have to come for the force between the two parallel current. My dear, here you have some theoretical question. You can just see the picture which I just gave in the top of the slide. You have, see, I have two wires, and here the first wire will carry the current IA, and the second wire carry the current IB, and you can see the direction of the current. When you have two parallel wires, when these two parallel wires carrying the current in the same direction, what will happen? There will be a force of attraction will happen. Keep this point in your mind. Whenever the current will be flowing in the same direction of the two parallel wires, what will happen? There will be the force of attraction will happen. Likewise, if you have two parallel wires, but the direction of the current is opposite to each other, by the time what will happen? It will have the force of repulsion. So please, my dear, this is a theoretical question. So please keep this information in mind. Whenever the direction of the current will be in the same direction of the two parallel wires, there will be the force of attraction. Whenever the current will be flowing opposite to each other to the two parallel wires, what will happen? There will be a force of repulsion. And we have one question, and by the time we will get some clear idea. And we already studied this rule in the previous chapter. What we studied, what is this, my dear? This is nothing but the magnetic force by the current carrying wire. So we know the current through this wire, which we know what should be the length of the wire, and we know what should be, because each wire, when the current will be flowing, what will happen? It will have the magnetic field. You have to see this picture. Each wire will have the magnetic field. Why? Because this wire also carrying the current, the second wire also carrying the current. That means the magnetic field of the wire A will affect the second wire. The magnetic field created by the wire B will affect the first wire. That means you have two magnetic field. So whenever you have two magnetic field, this magnetic field will affect the second wire, and this magnetic field, this wire magnetic field will affect the first magnetic field, first wire. So the same information was given here. So we are going to use what should be the force between the two current carrying wires. It's a proof how we got this relation. How we got this relation. This is what you understand from this equation, my dear. Force by the first wire on the second wire, the force of the second wire on the first wire. But the equation, you can see, if the same current will be flowing, then your IB, which is exactly equal to IA. That means when you have the same amount of the current, your IA, which is exactly equal to IB. Suppose if you have different current, it will be different. So what's the proof of this equation? How we got? You have to see these two equations. Just before we studied, what should be the equation for the straight line? That means the magnetic field for a long straight wire. So I am going to take this equation, and already we studied what should be the magnetic force generated by the current carrying wire. So I am going to compare these two equations. So what I'm going to do, my dear, listen this, just to see this picture, and you can just see this equation. So here I am going to take the first equation. What is this, my dear? This is nothing but the force by the first wire. So what should be the force by the first wire? The force, the magnetic force on the first wire will get affected by the magnetic field of the second wire. You can see this is your first wire A, this is your second wire B. So what will happen? The wire B magnetic field will affect the first wire. Likewise, the first wire magnetic field will get affected to the second wire. So that's what I just tried. Don't get confused about this A and B. So here this is my force on the first wire A. So that means the first wire A will get affected by the second wire magnetic field, and the first wire have the current IA, and the first wire have some length of the wire. So that means each wire have some length, and each wire carry the same current. That means better I can write again. This is my force on the first wire. So if you just see, the first wire have the current IA, and the first wire have the length. And what will be affected in the first wire, my dear? The magnetic field of the second wire, B. Likewise, the second wire equation, if you want to find the magnetic force on the second wire, what will happen? This wire B will have the current B, IB, and this wire have the length L, but should be affected for the second wire, the magnetic field of the first wire. That's what we just have this relation. You can see here. Now what I'm going to do, I'm going to take, this is my first equation. I'm going to take, this is my second equation, and then we are just directly substitute the value in this equation. So I'm going to take this, I'm going to substitute here. So this is the magnetic field affected by the first wire. That means the current carrying wire. So I'm going to take this equation, I'm going to substitute here. Likewise, in this equation, I'm going to use this first wire. So when you just substituting the first equation, this equation, when you just substituting this equation in both, you will get like this. Clear? So it's just simple thing. The magnetic, the first wire current will have the magnetic field, and that magnetic field will affect the second wire. Likewise, the second wire have the current, and when the current will be in the second wire have some magnetic field. That magnetic field will affect the neighboring wire. So if you just have a doubt, you can just see this picture. You can just see this picture. I have two wires, A and B, and my A wire magnetic field is black color. My B wire magnetic field is blue color. You can see this blue color will touch the first wire, and this black color is touch the second wire. That means the magnetic field of the second wire will affect the first wire. Likewise, the magnetic field of the first wire will affect the second wire. That's what we have this relation. My dear, generally we have the same current. That means your IA must be equal to IB. So you will get the same value. That means you have to squaring the value. So that means if you have IA, which is exactly equal to IB, what should be the value, my dear? It is nothing but I square. So when you just multiply these, you will get I square. So if you have the same current, it's no issue. You can just directly squaring. But if the current will be different, then you have to substitute each and every value. So we are going to use this formula in the first question, is what we are going to discuss in the next class. So right now the time, it's 9:30. So still how many minutes we have, my dear? I think today we have 9:50. Am I right? Am I right?
Yes.
Okay.
It is 20
So
minutes.
better. Okay. We have 20 minutes. At least we can just solve one question. We can solve one question.
Can you give the summary for the rules that we have?
So this is your first formula, Biot-Savart law, and we are going to use what should be the current for both wire just before we studied, and then we have Ampere-Circuited law. This is the magnetic field for the long straight wire. We have the magnetic field for the long straight wire. Clear? Clear? And one of the most important thing I forgot here, my dear, what I told you here, my dear, if the current of the both wire will be in the same direction, you have the force of attraction. Am I right? Am I right or not? When you have the force of attraction, what should be the magnetic field here? What should be the magnetic field here? Is there any magnetic field when you have the attractive force?
No, zero.
No.
Zero. So please, this is also one of the important question, my dear, theoretical question. So in this diagram, you have two theory questions. What are the two theory questions? Listen carefully. If you have two parallel wires, if two wires carrying the same amount of current in the same direction, you will get the force of attraction between the wire. When you have the force of attraction between these two wires, what will happen? There will be no magnetic field between the wire. Keep this point in your mind. Clear?
So doctor,
in the second,
B equal to 0.
Here B is equal to 0, because whenever you have the force of attraction, two wires will be attached to each other. Am I right? Am I right or not?
Yes.
So when you have the wire, two wires carrying the same amount of current in the opposite direction, what will happen? Force of repulsion will take place. By the time you will get some gap here. Am I right? Am I right or not?
Yes.
So by the time what you have, you will get some magnetic field. So please keep this point, because we have one question, and when we just solve that question, by the time you'll get some idea. So better I will do one thing. We have 3 questions. Out of these 3 questions, I will solve only one question right now, and inshallah we will solve the rest of the 2 questions in the next class. Clear? Clear, my dear? So better what I'm going to do, I'm going to solve the last question, which is related with this topic, Clear? Clear? Okay, we just go back to our third question. Now I will ask you a question. You must respond. Please take your calculator, because I need the answer from your side. Read the question first very carefully. What is given? Once you read, please, my dear, bring the diagram into your mind. Even though the diagram will not be given, at least please try to bring the type of the diagram in front of your eyes. Then only you will get the correct answer. You will get some idea. So let's just read line by line, word by word. And after that, I will draw the diagram. By the time you will get a clear idea. So what is given here, my dear? 2 long straight wires are parallel. That means I have 2 wires. So this is my wire 1. And these 2 wires are parallel. That means I have another wire. Two parallel wires. And these are separated 16 centimeter. That means what's the distance between the 2 wires, my dear? What's the distance between the 2 wires?
16 centimeters.
16 centimeter. Very good. And they are to carry equal currents. That means the current in the first wire, better I can put A and B. That means we have 2 wires, A and B. And these 2 wires, A and B, are parallel to each other. And these 2 wires are separated with a distance of 16 centimeter. And these 2 wires carrying the same amount of current. And by the time you have some magnetic field between the 2 wires, exactly to the center of the wire, how much magnetic field do you have? What should be the magnetic field here?
450 micro.
Micro Tesla. What's the meaning for micro?
10⁻⁶.
Okay, now tell me, my dear, first theory question. You have 2 wires, will have the current. Now, if you get any magnetic field here, the direction of the current of the 2 wires are in the same direction or opposite each other?
Opposite.
Very good. Why? What's the reason?
No,
Because
opposite.
there is magnetic field.
If the current will be moving in the same direction,
Yes,
there will be no magnetic field between the wire. Am I right?
Mm.
But here they clearly mention you have 2 wires, and these 2 wires will have the same current, and by the time the distance between the 2 wires is 16 centimeter, and by the time what you have some magnetic field in the half of the distance. So my dear, what's the half of the distance between these 2?
8.
Am I right? Am I right or not?
8.
So that means these diagram, because based on the
Yes.
information given in the question, it's clearly mentioned one current will be flowing in this direction, another current will be flowing in this direction. Am I right? Am I right? Am I right or not?
Yes, definitely.
Yeah.
If the current
Yes,
will
yes,
be
yes.
moving in the same direction, what will happen? If the current will be moving in the same direction, so what will happen?
No magnetic
There is
field.
no magnetic field.
So what will happen to the wire? Your wire will be coming like this. I will just draw the wire again. If the current will be moving in the same direction, what will happen? One wire will be like this because the force of attraction, and another wire will be like this. And what should be the magnetic field between this wire?
0.
0. Clear? Clear, my dear? Clear?
Yes, yes.
Okay. Now, let's just start reading the second part of the question. What is given in the second part of the question? Now, first question. Should the current be in the same direction or opposite direction? So what should be your answer?
Opposite.
Why?
Because
How you
there
can
is
say
magnetic
opposite
field.
direction? How you just say this is opposite
Because
direction?
we have
Because
a magnetic field.
they said between these 2 wires you have some magnetic field. That means if the current will be moving in
Yes.
the opposite direction, then only you will get the magnetic field. Otherwise, what will happen? Your magnetic field will be 0. So that means it clearly shows that the wire carrying the currents or in opposite direction. Correct? Correct? Is it clear, my dear? Clear?
Oh, yes, yes, yes.
Yes.
Okay. Now, in the second part of the question, that means the first part of the question is the theoretical question. In the second part of the question is what they ask, how much current is needed? So that means we must calculate the current. So this is the long straight wire. So what's the formula for the long straight wire, my dear? Go back to your numerical, the formula. What's the formula for the long straight wire? What's the formula?
B equal mu.
B, which
Mu
is equal to
naught
mu naught
I.
I over 2 pi r. My dear, here r is not a radius, r is the distance between the two wires. Clear?
Yes, yes.
Clear, my dear? Clear?
Uh-huh.
Distance between the magnetic field to the wire. So better we can just write the formula here. So that means I'm going to, for the second part of the questions, what I'm going to do, I'm going to write the formula for the long straight wire. What's the formula for the long straight wire? Mu naught I divided by 2 pi r. Am I right? Am I right or not? Clear?
Yes. Clear.
Okay. How many wires you have, my dear?
We have two.
That means you have to multiply with 2 here. Am I right?
Right.
Because each wire have the same formula. That means the wire A will have the formula mu naught I over 2 pi r, and the second wire also have the formula mu naught I over 2 pi r, because both are straight wire. Am I right? That's what I just multiply with 2. Clear? Clear, my dear?
Clear.
Okay. Now what we are going to find? What we are going to find?
Current.
So please rearrange this equation. So what you will get? Therefore, my current I, which is exactly equal to B
2 by
multiplied
R.
by 2 pi r divided by 2 multiplied by mu naught. Am I right?
Yes.
Am I right?
Yes.
Okay, now substitute the value. We have the magnetic field. What's the magnetic field value, my dear? What's the magnetic field? So current I, which is exactly equal to, what is our magnetic field? 450 micro. So that means 10 to the power of minus 6 multiplied by 2 multiplied by pi. And what's the distance of the first wire to the point B? What's the distance?
8 centimeter.
8. That means 8, and it's a centimeter. So we have to convert it to meter. That means 8 multiplied by 10 to the power of minus 2 and divided by 2 multiplied by, and the constant value of this mu naught, just before I told you, the mu naught is the constant value which will be given in the question, which is 4 pi multiplied by 10 to the power of minus 7. So in this place of mu naught, I am going to substitute the value 4 pi multiplied by 10 to the power of minus 7. So could you please calculate the value of the current? I want the answer from your side to check our answer. The unit for the current will be ampere.
I got 90.
90 amperes. Am I right?
Yes.
That's it. So let's we check our answer. We got 90. So that means our answer was correct. Clear? Clear, my dear?
Doctor, why you choose 8?
Because
Okay.
between the two wires, my dear, what's the distance between the two wires?
16.
What is the half of the distance?
8.
What's the mean? You can see what's the word here.
Halfway.
So what is the half of this A16?
16. 8.
That means from the wire A to the point
To B.
magnetic field, because in this point you have the magnetic field. So from the wire to the magnetic field you have 8, and likewise from the wire B to the
Second
magnetic
wire.
field you have another 8. Clear?
Right. Yes, it's clear.
So,
Clear?
doctor, it should be we use 16, but he said halfway, so we should. So we use
We
8.
use 8.
right?
Yes.
If he didn't mention halfway, we will use 16, right?
My dear, actually, we have to use halfway. Why? Because if you did not mention halfway, then it's meaningless. Why? Because because when the wire have the force of repulsion, then only at the exact center of the wire, because the distance between the two wires, we have some value. Exactly at the half of the distance only, you'll get the magnetic field. Am I right?
Yes.
So if there will be no halfway distance, where you will get the exact magnetic field? Generally, if you have two parallel wires exact at the center, that means exact half of the distance between the two wires, you will get the magnetic field. So for sure, this halfway value word will be given in your question. Clear?
Clear.
Clear, my dear? Is there any
Yes.
doubt?
Clear.
So two theory questions we apply here. What are the two theory questions, my dear? The first thing related with the direction of the current. The second thing, what is your second thing here? The magnetic field. If both wires carrying the current in the same direction, force of attraction will be there. By the time your magnetic field will be zero. But here they give the magnetic field. So if you got magnetic field, then the current will be in the wire is opposite to each other. So keep these 2 points in your mind. So whenever the current will be in the wire in the same direction, force of attraction will be there. When there is a force of attraction, there will be no magnetic field. Whenever there is a force of repulsion will be there, you will get exactly half a way distance between the two wires. You will get some magnetic field effect. Clear?
Clear.
Yes, total clear.
Okay, my dear. So I will just stop up to this because some students you have the lab classes. So please, my dear, I will stop up to this question. Inshallah, by next week I will complete this chapter, and inshallah I will immediately start chapter 30 because that chapter 30 is nothing. We are going to study only two definition, and for that two definition, I'm going to open some videos. When you just saw the video, by the time you'll get some idea. Clear? Clear, my dear?
Can I leave, doctor?
Yes, my dear, you can leave. I'm also going to leave now.
Doctor,
Yes.
I didn't log into the class until 9:38 or 9:37 because I had problem in my internet.
9:30. So okay, I just first of all I will see the list of the attendance, then I will check. Then I will just come for final decision. Okay, my dear.
Okay.
But for sure, my dear, I will enter the attendance before Sunday. So maybe within couple of days I will enter the attendance, and after that please come and contact me if there is any problem. Clear?
Okay.
Okay, brother. Assalamu alaikum.
Salam.